Hello everyone, welcome back. We have left parametric land. I think we've covered all that we need to cover. We covered the areas, we covered the arc lengths, we covered the derivatives, and we covered the curves themselves. All that's left to do is one more topic for single variable calculus. We're almost done. The second half of Unit 10, we will be covering polar coordinates. This will be a slightly more comprehensive unit than parametric curves, because these are a little bit more complicated because we're developing a new coordinate system, we're developing new curves, and we need to develop how to do calculus with them. Now, polar coordinates are an alternative coordinate system to rectangular coordinates. And we'll see that alternative coordinate systems can be very helpful when trying to perform integrals, and they can also be very helpful in multi-dimensions when you need to perform integrals as well. So anyways, we'll be covering an alternative coordinate system today. So normally, for the entirety of calculus that we've been covering so far, we've been dealing with an x-y coordinate system. So we have an x-axis and we have a y-axis. Now these form an orthonormal basis. That means that we have units that are perpendicular to each other and they generate squares. And with these squares, we can project these across the whole plane, which makes things very nice. However, there are some cases where we need other coordinate systems. And it should be mentioned, the xy coordinate system very nicely describes many functions that we like to draw. So all of our polynomials, even implicit functions, or implicit relations that we like to draw, we can draw those too in this xy method. However, sometimes we need to determine some more complicated integrals or derivatives, or we need to maybe transform how we view a function so that we can perform derivatives and integrals more easily. We need to develop a new coordinate system. So the coordinate system that we develop is the polar coordinate system. Now the polar coordinate system basically entails, instead of using just these units, we use circles and magnitudes. So we have one axis, we call this the polar axis, and we call that R. And R will be swept out by some sweeping angle, which we will call theta. So we can describe any point as long as we know its magnitude and angle swept over the polar axis. Now, that's something that's very interesting, and allows us to describe functions in a very interesting way. Now, how do we do this? So basically, what we are doing is we are switching from an xy coordinate system, which is based on a position and a height, or a position entailing a distance and a height. So we have a point x0 and y0. But we can also describe this by a magnitude r0 and an angle theta0. These are both perfectly valid ways of describing such a point. So how do we convert between these two very important coordinate systems? Well, we can look at relations trigonometrically. Let's say I know r0 and theta0. So if I know r0 and theta0, then I can find x0 by taking r0 cosine of theta, and I can find y0 by taking r0 sine of theta0. So we get x equals r cos theta and y equals r sine theta. So if I am given a function, or a relation including x and y in there, then I can convert that to f of r and theta by maneuvering this around such that x equals r cos theta, y equals r sine theta. Or wait, sorry, this is the other way around. If I'm going backwards to f of x, y, and I start with f of r theta, I can convert that in such a way. Anyways, we can go the opposite way as well. If I start with f of r theta, or if I'm ending with f of r theta, I'm kind of doing this backwards. You can use the following relationships. So in order to find r naught, we just take the Pythagorean theorem. This is the hypotenuse of a triangle, so that x naught is one side and y naught is the other side. So we take r squared equals x squared plus y squared. If I want to find theta, well, we can use the inverse tangent function. So tangent of theta is equal to y over x. And that brings us to our r of theta. Anyways, So there we have a relationship. R is equal to the square root of x squared plus y squared, and tangent of theta is equal to y over x. Now, this allows us to convert between polar coordinates and rectangular coordinates, and vice versa. So we'll make it vice versa. Anyways, now what we'd like to do is an example. We're going to do a couple of examples. So let's just convert the following to polar coordinates. So we've got 1, negative 1. So this is a Cartesian coordinate that represents the unit, or wait, no it doesn't. It is in a different position on the coordinate plane. So we got 1, negative 1, so it's about there. I want to find out a way to represent that in the polar coordinates. So the way we do that is we use r squared equals x squared plus y squared, and tangent theta is equal to y over x. So what we do is we plug that into the formula. So r is going to be 1 plus 1 square rooted, which is equal to root 2. Should be very obvious by using the Pythagorean theorem that we have. Then tangent of theta is equal to negative 1 over 1, which is equal to negative 1. So we have determined polar coordinates. We just need to find theta. So for theta, we can recognize that this is going to be in the 4th quadrant of the coordinate plane. So it's going to be this angle here. It's going to be this angle here. Or it could alternatively be this angle here. Depends. I'm going to personally go with the negative pi over 4 option. So we will get theta equals negative pi over 4. So this r of theta is equal to square root of 2, comma, negative pi over 4. So that is an equivalent way of representing this rectangular coordinate in polar form. All right. I'd like to do another example. I'd like to discuss actual polar curves. So it turns out that you can make functions of these guys. So you use theta as your new x, and you use r as your new y. So for every theta, it models a certain magnitude. So you have r of theta equals some function of theta. So basically, what we can do is we can draw these out. Obviously, the brute force method works by plugging in a ton of points to graph it, just like we did with parametric, but there's also a couple of smart ways to do it as well, kind of similar to how we eliminated the parameter back in a couple videos ago. So I would like us to sketch r equals 2 cosine of theta. Okay, now this looks like something crazy. We don't really know what that means. However, there are a couple ways that we can do this. The first thing that we can do is we can graph y equals 2 cosine of x. We can look at the different x values and the different y values, and then we can think about wrapping those y values around on the polar curve, on the polar system. The other way to do it is to recognize the relationships that we have. We know that we know x squared plus y squared equals r squared. We know tangent of theta is equal to y over x. We know x is equal to r cos theta. We know that y is equal to r sine theta. So you can use these facts to transition this from something of a polar equation to a rectangular equation that we know and love. We all know how to graph these rectangular equations a lot more easily than the polar equations. So what we do is we take r equals 2 cosine of theta, and we are going to plug in, we know cosine of theta. So cosine of theta is equal to x over r. So what we get is r is equal to 2x over r. We can move the r squared over here, and then we get r squared is equal to 2x. We know r squared is equal to x squared plus y squared. We're going to move the 2x over, so we get x squared minus 2x plus y squared is equal to 0. Now we will complete the square, and in doing so, we will get the equation of a circle. So we will get x minus 1 squared plus y squared equals 1. Okay, now this is something that is very, very interesting to think about. So anyways, what we get from this is we get a circle of radius 1 that is centered at 1, 0. So our radius is 1, and we are centered at this point, 1, 0. So we get something that looks something like this. And that is what our graph looks like. Now I'm hoping that this was just kind of a little refresher on how to deal with polar coordinates. I know most of you probably have already learned this, but we're going to get in the good stuff in the next video where we'll discuss the actual derivatives, tangent lines of these polar curves in a similar way to how we discussed it with parametric. But we're going to spend a little bit more time discussing integrals and integration because it's a little bit more complex than it is for the parametric equations. Anyways, thanks for watching. We'll see you in the next one to talk about the polar derivatives. Thanks.